Hi there, this is Kevin Oldknow, and I'm pleased to be presenting at this year's Wheel-Rail Interaction Conference. In this brief video, I'll talk a little bit about creepage at the wheel-rail interface. So why is creepage at the wheel-rail interface so important? Well, it's related to a wide range of important phenomena, including locomotive adhesion, braking, vehicle steering, curving forces, wheel and rail wear, rolling contact fatigue and thermal defects, noise, and corrugations. To get a sense of what creepage is, we can first consider this simplified view of the wheel and rail. Now in free rolling, a wheel would rotate 100 times to travel a distance of 100 circumferences. We can contrast free rolling with positive longitudinal creepage, where we might imagine a driving torque applied to the wheel as we see here. And that driving torque creates a small relative motion between the wheel and rail at the interface. Now at 1% positive creepage, for example, a wheel would rotate 101 times to travel a distance of 100 circumferences. Looking now at negative longitudinal creepage, we can imagine a braking torque applied as you see here. That braking torque will again create a small relative motion between the wheel and rail at the interface. At 1% negative creepage, a wheel would rotate 99 times to travel a distance of 100 circumferences. In addition to longitudinal creepage, we can think about lateral creepage. Now looking here at a two-axled vehicle as it negotiates a sharp curve, we can see that the trailing axle tends to stay radially aligned with the curve, while the leading axle develops an angle of attack. Because of that angle of attack, for each unit of forward motion, the leading axle has to slide just a little bit sideways, creating a relative motion again between the wheel and the rail at the interface. For example, at an angle of attack of 0.57 degrees or 0.01 radians, we would get a lateral creepage of 1% at the leading wheel set. The last type of creepage that we'll look at is spin creepage. Now if we imagine 3 points on the surface of a conical wheel, shown here in red, green, and yellow, we can imagine that as that wheel turns and the points approach the middle of the contact area, they're going to move at slightly different speeds to get there. If we consider the green point to be in neutral or free rolling, then towards the smaller side of the wheel, because of the smaller radius, our red point is going to be moving more slowly and will be in braking or negative longitudinal creepage. On the other side of the contact area, where the wheel radius is larger, our yellow point is going to be moving faster and it'll be driving or in positive longitudinal creepage. So if we imagine that distribution of speeds across the complete contact area, we can see that the net effect is as though the wheel was spinning relative to the rail. The net creepage vector, then, at the wheel-rail interface is generally a combination of all the creepages that we've looked at: longitudinal, lateral, and spin. At this year's WRI Principles course, I'll be presenting a 3-part seminar on wheel-rail interaction fundamentals. In the 3 parts, I'll cover the topics that you see here. I very much look forward to it and hope to see you there.